Calculus has a lot of really neat application problems. One of them is called a related rates. Let's show you kind of this problem and what related rates are. Well, we've got to read the question first. So, you have a conic container, meaning a cone, like an ice cream cone. Yes, I love ice cream. That is 6 meters tall. Oh, that's a huge, huge ice cream cone. Okay, but it's a cone container, really, really tall one, and that has a diameter of 4 meters. All right, let's draw a picture of this because you're going to need it for the problem. Anytime you do related rates, you actually want to draw pictures. It just really helps for the visualizing of what's going on. Okay, so we're going to draw a nice little cone. All right, and from this cone, hopefully you realize we have a 6 meters tall. So that means is, let's call this the diameter, cross. And we said it's 6 meters tall, so from here to the bottom, we said is 6 meters. All right, and what is the diameter? 4 meters. So across here is 4 meters. So we have 6 meters up and down and 4 meters across. So what would the radius be? What's that? Can you tell that R is equal to 2 meters? Because if you look right here, isn't the whole thing 4 meters, so the radius is 2 meters? Just usually when you do a circle, we use with radius more than diameter, but just that'll be a reference for later. So we got this cone, really, really huge, huge cone. All right, let's keep going. All right, it is filled to the top with water. Ooh, that's a lot of water. When you unplug the container, so we're going to unplug it down here, to get water out of it, the water empties at 5 cubic meters per hour. So water is going to drain out of this at 5 cubic meters per hour. All right, makes sense. How fast is the water level changing when it is 3 meters high? So say the water is 3 meters high, which if this is 6, isn't 3 meters basically halfway down? So isn't the water level going to be 3 meters high? Okay, so this is going to be 3 meters high. All right, and we're wondering, okay, how fast is this water level changing? All right, at 3 meters high. Okay, if at that point the diameter is changing at 4 meters per hour. So this diameter is changing at 4 meters per hour. That's a lot of information, isn't it? All right, real quick. What would that radius be? If this is 3 meters high, and this is 6 meters high, if this is 4 meters across, isn't this cone half the height of this one? So if the diameter is 4, can you tell that this diameter is going to be 2 meters? Can you tell the diameter is 2 meters across and 3 meters down for this cone at this point when we're trying to find the information for the problem? Can you kind of see what's going on here? Now, how do I know that that right there is 2 meters across? Well, you could do a proportion. And a proportion looks like this. 6 height to diameter is equal to height to diameter. Okay, height to diameter is equal to height to diameter. The reason you can do that is there is if you kind of bring this line down, put a right triangle here, it's called similar right triangles because in geometry you learn about similar right triangles, and so these triangles would be proportional because of similar right triangles. So the relationship of 6 to 4 is the same as 3 to blank, and if you solve this proportion, you will get 2. So basically 6 over 4 is the same as 3 over 2 if you reduce it. Anyway, so what you might be saying, why is he making this shape and all this information? You'll see in a second. You got to kind of draw the picture with what you know and what you see. The pictures are very important in a related rates problem. Also, you're going to run into a formula you deal with in all related rate problems. Because what's going to happen with this formula is you're going to take the derivative of it. And here's why. The question is saying that it's emptying at 5 cubic meters per hour. Now that's a rate. Hopefully you understand that. That's a rate. And the diameter is changing at 4 meters per hour. That's another rate. All right. And it wants to know how fast is the water level changing. So it wants to know how fast the water level is changing, but it's giving you 2 other rates. So we're trying to find some rates. And if I want to find rates, and related rates, aren't they all kind of related due to the formula? I'm given rates, and I want to find a rate. Well, rate is a derivative. And if you look at this, isn't this meters per hour, cubic meters per hour? So aren't you finding a rate of this volume per hour, per time? Okay, so in a related rate problem, you're going to find an equation, a formula, and you're going to derive it in respects to time. That's the key. So you need a formula, and most likely you need a picture to visualize what's going on. And you're going to take the derivative, and then you're going to plug in a whole bunch of stuff. You'll see. So here we go. We're going to derive this in respects to time. Here's how it looks. We're going to have dV dt. That's the rate of the volume in respect to time. I derive this implicitly. Equals. I'm going to take this pi over 3 and just put it out front. That is a constant. When you take derivatives, you can put constants out front. A lot of people forget pi is a number, 3.14. So you can just pull it out as a constant. It's very easy to forget that. Anyways, so I leave that out. Now, if I'm taking the derivative of this piece, do you see a product rule? All right. So the product rule, what's the derivative of r squared? Well, that would be 2r. But chain rule, don't you derive the inside? So what's the derivative of what's inside? R. Or derivative of r is in respect to time. It's not derivative of r. It's not r prime. It's actually dr dt. Chain rule, derive the outside. Now derive r. dr dt. And then for product rule, now I need that times h. Plus, leave the first piece. So leave r squared. And derive h. Well, the derivative of h is just going to be dh dt. Okay, that's a funky looking derivative. Well, yes it is. It looks very implicit, except with implicit derivatives, we derive in respect to x, or one of the variables in the equation. Here we're not deriving by any of these letters in the equation. We're deriving in related rates always in respects to time. How do you know when a related rate problem is in front of you? It's when they say in respects to time, when they take a formula and put time into it, and you have a rate. Okay, I have this derivative here. Now I could try to simplify this, but right now I'm not going to. What I'm going to do is I'm going to read the question again and start plugging numbers in and then solve for what I'm asking for. Because within this equation, I could plug numbers in for almost every single letter. Watch. Here we go. The first thing we run into is these two numbers, but that's just the parameters of it. We keep going. Let's see. Here. It's emptying at 5 cubic meters per hour. Now if it's emptying and it's cubic meters per hour, isn't cubic meters volume in respect to time? So wouldn't that be dV dt? So wouldn't that be 5 cubic meters per hour? There we go. So I can go ahead and plug in 5 right here. All right, we're going to see that happen. We're going to do that right now. I'm going to plug 5 in right there. I'm going to leave pi over 3. Okay, I'm going to leave the 2. All right, because the 2 right there. And then, okay, next, let's do another one. Let's see. How fast is the water level changing? So the water level changing, they actually want to find the rate at which the height is changing. So the question is technically finding dH dt. Aren't we trying to find the rate at which the height is changing? So this is the final answer. We'll come back to that. That's going to be my final answer, which that is what we're going to try to find. Okay, and okay, when the height is 3 meters. Well, if the height is 3 meters, well, don't we know the height is 3 meters? Isn't that what we're trying to find it at, 3 meters? So can I go over here where there's an h and plug in 3. Okay. If at that point the diameter is changing at a rate of 4 meters per hour. Oh, we just got another rate of change. But it's diameters. I have radiuses. Don't I have dr dt? Well, if my diameter is changing at 2 meters, okay, no, sorry. If my diameter is changing at 4 meters per hour, the diameter is 2 here. But if the diameter is changing at 4 meters per hour, what would the radius be changing at? Can you think about that? What is the radius changing at if the diameter is changing 4? Well, isn't the radius half the diameter? So wouldn't the radius be changing at 2 meters per hour? Okay, so we have dv dt, dr dt. Okay, dr dt right there. So what is that going to be? We said dr dt is 2, so I could plug a 2 right there. Alrighty. Remember, there's a plus. We want to find dh dt. That's what we're trying to find. Okay, now we are. Oh, what's the radius? It's not given. Oh, no. Well, it's not given, but do you remember me talking about why we wanted this 2 here? There's a reason. Well, if that's 2 diameter, wouldn't the radius be 1? So isn't my radius simply 1 meter at the point where the question's asking? So can I go and put 1 right there and 1 squared right there? Can you see here? I can solve this for dh dt, and I can find the rate at which the height is changing. Alright, so let's do that. To finish this, let's simplify. Ready? Keep the pi over 3. Let's multiply all that together. What does that give us? 2 times 1 times 2 times 3. 12. 1 squared, that's a toughie. 1. So plus dh dt. Alrighty. Can we finish this? Yes, we can. So what would be the next step to solve this? Well, could we multiply, or can we get basically dh dt by itself? Alright, what would be the best way to get dh dt by itself? Well, I'd probably divide by pi over 3, or wouldn't that also mean to multiply both sides by 3 over pi? If I multiply both sides by 3 over pi, won't that cancel? So what you're going to see here is I now have 15. Okay, this is leading over here. 3 times 5 is 15 over pi is equal to, remember, this cancels this cancels with this, 12 plus dh dt. Alright, and then if I want dh dt, don't I simply, last thing is minus the 12 over? So what do you see dh dt is? Well, it's kind of an ugly number, but it's 15 over pi minus 12. Wouldn't that be it? And if you want to put the units, which we probably should, wouldn't that be meters per hour? If you had a calculator, could you get the exact value of that? Okay, that would be a decimal value. We could get the exact value in meters per hour at which the height is changing. Now it seems like a lot of work, and they are. This is probably a little bit harder problem. There's a lot of easier ones out there. Now, let's do a recap. Related rates. You find a formula, and you're taking the derivative in respect to time. You're probably going to want to draw a picture. Okay, once you derive it in respect to time, you then have to look through the problem and find all the pieces except for what you're looking for. And you're usually looking for either one of the dt's, one of these 3 or whatever, how many dt's there are. You're finding one of the rates in respect to time. And so you got to find all the variables, plug them all in, and solve for the piece you want. Sometimes the information you need is obvious. Sometimes you have to do some manipulation to get it. It all depends. There's different ways. But related rates, taking derivatives in respects to time, plugging in data, finding the last piece left. Good luck with them, and don't give up when they get complicated.